Okay, these are what we call sinusoidal functions. Okay, it's a big fancy word that just like pretty much comes down to we're talking about sine and cosine. Okay, sinusoidal functions are a specific type of periodic functions. We can have any. The definition of a periodic function is just that it repeats itself every set amount of x values. Okay, so you can have something. It doesn't have to be a trig function to be a periodic function, but those are the most common periodic functions that we talk about. Now, they are called periodic functions, and we'll talk about it here in a second why. Let's start with filling in some values here from what we know off of the unit circle. Okay, so our x-axis here are all of our angles. Hopefully you can see it there on your paper. We've got 0, pi over 4, pi over 2, 3 pi over 4, etc. We also have negative values. Okay, so who can tell me what the sine of 0 is? What's the sine of 0? From the unit circle. 0. The sine of 0 is 0. Not where is sine equal to 0, but what is the sine of 0? When your angle is 0, the value of sine is 0. Okay, what about the sine of pi over 2? 1. How about the sine of pi? 0. I'm so glad we learned that unit circle so thoroughly. The sine of 3 pi over 2? -1. I'm hitting the easy ones, guys. I'm hitting, the four corners, so to speak. How about the sine of 2 pi? 0. Okay. Now, I could go in, I could fill in pi over 4. Okay, the sine of pi over 4 is what value? Square root 2 over 2. Obviously, we don't have square root 2 over 2 here on our graph. We actually do need the decimal value of it if we wanted to graph that. Okay, the square root of 2 over 2 is about 0.7. So we'll put it about right here. The sine of 3 pi over 4 is the same thing. Okay, the sine of 5 pi over 4 is the same thing, it's just negative. The sine of 7 pi over 4 is also that negative 0.7. Now, you were supposed to look at the graph of sine in Math 3, so hopefully this is starting to look a little familiar to most of you. Now, there is nothing special about the x values that I just chose. Okay? I just picked the easy ones, and I had my graph marked off in increments of pi over 4. I could have used pi over 3. I could have used pi over 2. I could have used an angle that wasn't even on the unit circle. Okay, so we can find the sine of I don't know, pi over 12. Okay, pi over 12 is not on our unit circle. It's not one of our special angles, but that doesn't mean that it doesn't have a value of sine. Okay, it does have a value. It would be 0.2, and let's see here, that would be what? About right here is where that would be if we were to graph it that way. Okay, so based on what you know and what we've got so far, you should start to see this curvature here for our sine function. Okay, and let me remind you, we tend to forget this, okay? The graph is the set of all the possible y values. So we tend to talk about the whole numbers, or in this case, the special angles. We tend to focus on the things that are easy to graph. But what I was trying to point out with the pi over 12, or I could have done 5 pi over 8, okay? Those aren't on our unit circle, but they still have a value for sine, even though they don't have a special value as we're used to getting it from the unit circle. Now, we can continue, okay? We can keep going. It doesn't stop at 2 pi. Sine does not stop having value after 2 pi. That's just more than one revolution. So 9 pi over 4 is what we've got over there. Guess what? It's the same value as pi over 4. If you found the coterminal angle for 9 pi over 4, guess what it is? Pi over 4, because you subtract 8 pi over 4. 5 pi over 2 is the exact same thing as pi over 2, because when you find the coterminal angle, You subtract 4 pi over 2, so you get the same thing. So this is a periodic function because it repeats the same pattern over and over again. If we go in the opposite direction, if we talk about negative angles, okay, negative pi over 2 is the same thing as positive 3 pi over 2, so its value is negative 1. So we can come right over here and connect our graph. Negative pi is the same thing as positive pi. Okay, add 2 pi to it, you get positive pi. It's the exact same angle, it's just a coterminal angle. Negative 3 pi over 2 is the same as pi over 2, so it has the same y value at positive 1. Negative 2 pi is the same as 0, or 2 pi, so it has a y value of 0. And I can keep repeating this pattern over and over again as many times as I need to. Oh wait, that's in the wrong spot right over there. Okay, so negative 5 pi over 2 would also be negative 1. 3 pi would be 0. There we go. All right, so it just keeps repeating itself over and over and over again. Now, what we focus on is we always focus right here between 0 and 2 pi. That is always our focus because that is one complete cycle, okay? One complete cycle here. And we call that the period, okay? One complete cycle. The period here is length 2 pi, standard, okay? The standard period here would be 2 pi, okay? We started 0, 0, we hit our maximum, we hit our minimum, and we end up back where we started. That's what we consider one complete cycle between 0 and 2 pi. So that would be our period. The frequency is how many cycles are completed in 2 pi units. So the standard frequency is 1. Okay, the standard frequency is 1. Today and tomorrow we'll start looking at not just the sine of x, but the sine of 2x and moving it around and stuff like that. So it'll change that frequency, but the standard frequency here is 2 pi. Now, I want you to go ahead and make a note about this. If you had to calculate it, it would be 2 pi divided by the period, okay? 2 pi divided by the period is your frequency. That's how you find it. So in this case, the period is 2 pi, so 2 pi divided by 2 pi is 1. Okay, that's how you would calculate the frequency. Okay, let's go back to the beginning of what I've got under your graph there. We need to fill in domain and range. The domain of sine of x, okay, any guesses? All real numbers, okay, all real numbers, because we don't have any discontinuities here, okay? There are no gaps in our graph. If we start on the left side and start tracing it, we're never going to have to pick up our pencil to continue the function, and it continues on forever. So the domain is all real numbers. How about our range? -1 to +1, inclusive, okay? It equals -1. -1 is its minimum value. +1 is its maximum value. Now, again, this is just the standard. We will look at, well, what happens if we throw extra stuff into our equation here, but this is the baseline here for our trig function. Okay, the y-intercept of sine of x would be 0, 0, the origin, okay, which also means that is one of our x-intercepts, but we have a lot of x-intercepts, okay? We've got x-intercepts at 0, pi, 2 pi, negative 2 pi. So here's how we're going to write this. We're going to write it as we'll do pi k comma 0, okay, because our y value is always 0 for our x-intercept, right? Y is always 0. So the x values, k is an integer, okay? K is an integer. You need to write that below your point here. So what it's saying is if k is 0, pi times 0 is 0. That gives us our x-intercept right here, the origin. If k is 1, then pi times 1 is 1 pi. So there's our other x-intercept. If k is 2, 2 pi gives us another x-intercept. It can be negative, -3. That would give us -3 pi. That would give us the x-intercept over there. So that gives you all the sets of x-intercepts because we can go infinitely to the right, we can go infinitely to the left. Okay, these keep on repeating. There's an infinite number of x-intercepts for the sine function. Okay? Now, the amplitude. Okay, the amplitude is defined as the height of the function from the midline. Okay, it's the height of the function measured from the midline. Or we'll say height of the graph from the midline. Or you can find the total height from bottom to top and divide it by 2. You're going to get the same thing. So in this case, it is 1. Okay, in this case, it is 1. We are going to look at changing that in the future, but right now it is 1 because our midline, it's cutting our function in half. Okay, so in this case, our midline would be the line y equals 0 is our midline here. Again, we will also look at shifting that around, but the standard is that it is the x-axis or y equals 0. So if we go from the midline to our maximum, we get 1, or from our midline to our minimum, we get 1. Those should be the same distances. Okay, if it's right there in the middle, kind of makes sense. All right, so that is the sine of x. Let's flip our paper over and let's look at cosine of x. Okay, cosine of x has a very similar shape. Bless you. Very similar shape because sine and cosine have very similar values, right? But just slightly different placement because what's the cosine of 0? 1. Okay, so instead of starting on the origin, we start up at our maximum value. Instead of starting on the midline, sine of x starts on the midline, cosine of x starts at the maximum. Cosine of pi over 2 is 0. Cosine of pi, -1. Cosine of 3 pi over 2, 0. And cosine of 2 pi, 1. We can go in and we can fill in values for pi over 4. It's the same thing as sine. Square root 2 over 2 or 0.7. 3 pi over 2 is negative square root 2 over 2 or negative 0.7. 5 pi over 4, same thing, negative. 7 pi over 4 is positive. So it has a very similar shape. These are curves. Okay, make it look as curved as possible. And we'll just connect the dots with straight lines. Y'all would be surprised at the things I've seen. Okay, now it doesn't look too terribly much like sine right now, other than the fact that it's curved. But if we do continue the pattern, we will begin to see it looking more like our sine graph. Okay, so continue it just like we did the sine by repeating those values. Okay, negative pi over 2 would be at 0, negative pi is at -1, negative 3 pi over 2 is at 0, negative 2 pi is at 1. Okay, connect those there. And keep going. Okay, so we see that same periodic, that same repeating behavior. It looks a lot more like sine now, doesn't it? It's just kind of shifted over a little bit from the sine graph. So a lot of these characteristics are going to be the same, okay? We still focus between 0 and 2 pi, okay? That's still going to be our focus, that one complete cycle here. This cycle just starts at its maximum, goes through its midline, hits its minimum, midline again, and returns back to where it started. Okay, the key is getting back to where it started, hitting all the values, and then getting back to where you started at to complete one cycle. So this also has a period of 2 pi. Its frequency right now would also be 1 because it completes one cycle in 2 pi units. Its domain is also all real numbers. We can take the cosine of any angle. It does not have to be on the unit circle. The cosine of 5 degrees. It exists. It's just not nice and convenient to graph. Okay, the range, any different? Nope, same thing, okay? Just different places where we achieve those values, but it's still -1 to 1. The y-intercept is different. It is 0, 1 is our y-intercept. Our x-intercepts, we still have a bunch of them. They just occur in some different places. Okay, we've got pi over 2, 3 pi over 2, 5 pi over 2. Here's how we write that. We start with the pi over 2, and we add pi k. Okay, so k is still an integer, but we're not starting at 0 this time. We got to start at pi over 2 and add from there. So we either add pi to it, we get 3 pi over 2. We subtract pi from it, we get negative pi over 2, etc., etc. The amplitude here is still 1. The midline is still y equals 0. That still cuts us in half right here. And when we measure from that line to the maximum and or the minimum, that distance is still positive 1. No differences there. Okay. I feel like there was something else I was going to say. I think I actually hit all the points this time. All right.